this group geometry is called trigonal bipyramidal. It's trigonal bipyramidal because we can look at this as forming two pyramids with a triangular base. So one pyramid goes up to this, the other pyramid goes down to this. And so this is one way of looking at this structure. Another way of looking at this structure would be something like this, where one coming out and one going in. And so it forms a trigonal planar arrangement here. And so we use the same three holes that we use for trigonal planar, but we're using the top and the bottom now. The top and the bottom holes are like this. When we look at this, is this spherically symmetric? What it means to be spherically symmetric is this. No matter which group you grab, it all looks the same. This turns out not to be spherically symmetric. We have two groups here. The one coming up here, this is called an axial group. This is called an axial group here. It forms an axis that we can spin to see this triangular or trigonal planar arrangement. And so each spin of 120 generates the same structure. And so this is what we call a symmetry axis. These positions here are called equatorial. And so we have three equatorial positions that forms the trigonal planar arrangement, and two axial positions here. So three equatorial, two axial. Now, is there a difference? Well, there is a difference, because if you grab an axial, what do you see? If you grab an axial position, what you see are three groups at 90 degrees, those are the neighbors. However, if you grab an equatorial, what do you see? Well, we have two 90s and two 120s. And so why does it matter? Well, it matters because of the space. Lone pairs take up more space. And so lone pairs, it makes a difference. Should you put the lone pair in an axial, or should you put the lone pair in an equatorial? And so which one do you think has more breathing room? An equatorial position or an axial position? Well, you could use some geometry to figure it out, but it turns out that 3 90s is more crowded than 2 90s and 2 120s. And so the lone pairs go in the equatorial sites, not the axial. That's because the repulsions are going to be minimized that way. And so if we have trigonal bipyramidal, then the geometries are going to be trigonal bipyramidal if we have bonded atoms in the same arrangement. An example of that would be something like SF, no, not SF, let's do CLF. Oh, let's see which one they did. Oh, I know which one they did. PCL5. So let's do PCL5. We do the Lewis structure for PCL5. We see it has 5 groups. We want to arrange the groups in a trigonal bipyramidal arrangement to minimize the repulsions. And the 5 groups are all going to be single bond groups. So we can build this. You take a brown one and attach 5 green ones. We'll have PCL5. If we look at the geometry of the bonded atoms, the geometry of the bonded atoms match the geometry of the groups. So this is trigonal bipyramidal molecular geometry. Now we're going to label the chlorines, because the chlorines occupy 2 types of sites. These 2 chlorines at the top and the bottom occupy axial sites. These 3 occupy equatorial sites. So I'm going to label them A for axial, E for equatorial. And therefore we can figure out the bond angles. And so if we go axial to phosphorus to axial. So an axial, the axial angle should be what? 180. Actually, we don't expect any distortions to that angle, because these three will push it up and these three will push it down, so equal and opposite. And then we'll go chlorine equatorial to chlorine equatorial. An equatorial to equatorial angle, well, that's the trigonal planar arrangement of 120 degrees. And the last angle is going to be axial to equatorial. And so the axial to equatorial angle is going to be 90 degrees here. And so these are the bond angles that we expect for this. And we don't expect any distortions to this particular structure. That's PCl5. You can build PCl5 and see what it looks like. Yeah. The next geometry that we're going to observe is something called seesaw. Seesaw, an example of seesaw would be SF4. When we do SF4, we have a trigonal bipyramidal arrangement of groups. We have 4 bonds. And so the 4 bonds, 2 of the bonds I'll put in axial. 2 of the bonds I'll put in equatorial. And I'm going to use these 2 equatorial sites here. And then the lone pair I'm going to put in the plane in this equatorial site. And so this part, this fluorine, this sulfur, this fluorine, and the lone pair are all in the plane. Okay, so just pull off one of the bonds and replace it with a lone pair, and we generate this. The reason this is called seesaw is if you tilt this and stand the molecule up on these 2 fluorines, then it's like a seesaw. You know, these are the legs of the seesaw, and this is the plank of the seesaw. And so it's a seesaw structure. That's with one lone pair. We have that. And so let's label that. Well, the lone pair goes in the equatorial. This is an axial fluorine, this is axial, this is equatorial, this is an equatorial fluorine. And let's figure out the angles here. So if we go fluorine axial to fluorine axial, the axial to axial angle should be 180 degrees, ideal. But we have this lone pair here, and this lone pair causes greater repulsions because it's concentrated on the sulfur, and that's going to push these 2 fluorines in. So if these 2 fluorines get pushed in a little bit, then that's going to widen this angle and narrow this angle. Bond angles are always given as the narrowest angle, not the widest angle. And so the narrowest angle, well, it's going to be distorted a little bit, and so we'll just say about 178 degrees as far as distorted. Again, these are just total guesses, but it's better than going less than 180, because less than 180 is anywhere from 0 to 179. It's too big of a range. And then let's go equatorial to equatorial. The equatorial angle should be 120, because that's in the trigonal planar. But because of this lone pair here, we expect a distortion here and a distortion here. So it distorts this one 2 degrees and distorts this one 2 degrees, then there's going to be a 4-degree compression here. And so we'll just guess around 116 degrees for this. Again, these can be way off too, because it depends on how big the atoms are and other factors. The distortions might not be so significant or as predicted. And then we have the axial to equatorial. And so if we go axial, sulfur to equatorial, this looks like iron. Let me change this. And so axial to equatorial. Then it should be at 90 degrees. We expect some distortion because of lone pair, so we'll just say about 88 degrees. Plus or minus a bunch. And so that's the seesaw geometry. The next geometry we have for this group, this is the next molecular geometry, is T-shape. T-shape is when we have two lone pairs. Those two lone pairs are going to occupy equatorial position. And so let's look at a T-shaped molecule like ClF3. But before I do that, I should mention something. I forgot to mention it. PCl5, does phosphorus have an octet in PCl5? No, it has more than an octet. Is that okay for phosphorus? Yeah, it's okay. And so why should something like that happen? Something like that happens to maximize the number of bonds. And when you maximize bonding, you increase stability. And so this is the reason why. And so it's going to cost energy to expand the octet, but you get energy in return by forming more bonds. And so the same thing here, kind of maximizing bonding. Because normally sulfur is like oxygen. Oxygen likes to form two bonds, right? And oxygen only forms two bonds, either two singles or one double. Sometimes oxygen forms three bonds, but the charge on oxygen changes. It's no longer oxygen neutral, it's oxygen plus, like in hydronium. Well, here, sulfur normally forms, but we're increasing the number of bonds here by expanding its octet. Well, ClF3, this is kind of weird because fluorine only forms one bond, but chlorine can form more than one bond. Right? Chlorine's a lot bigger atom than fluorine, a lot less electronegative, even though it has the highest electron affinity. We don't really use it for much. Electron affinity is just used for Hess law type calculations. And so ClF3, not necessarily for prediction of chemical reactivity. We got two lone pairs. The two lone pairs are going to go into the equatorial. And so what I'm going to do is I'm going to put the three fluorines in the plane like this. And so two of the fluorines are going to go axial. And one goes equatorial in plane. That means one lone pair sticks out equatorial out of plane, and one lone pair sticks in equatorial in plane. Going in past the plane. And so this is what we call T-shape. Actually, I wrote it there. And let's look at the angles. So you can build this, make sure it looks like a T. And so when you build this, you got to make sure the axial and the axial have bonds, and one of the equatorials has a bond with it. And so what we'll do is we're going to look at the axial to axial angle. The axial to axial angle should be 180 degrees. So it's 180 ideal, but it should be distorted. You got two lone pairs here. Those two lone pairs are going to compress the angle here, maybe by about 2 degrees each, so we'll guess 176 degrees as the distorted angle. And then we have the axial to equatorial angle. So when we look at the axial to equatorial, this angle is normally 90 degrees. But the lone pairs are going to compress it here. And so we'll just say 88, 86 degrees. 86 might be a little extreme. Anyway, it's a guess. So we'll just do it. We're trying to estimate the structure and the angles the best we can without doing any calculations. It's T-shape. If we have three lone pairs, then all three equatorial sites are going to be occupied by lone pairs. Let's see which one that is. That's CF2, I think. Look. That's CF2. XeF2. This is a very unusual compound because xenon is a noble gas. Noble gases aren't supposed to react. But the thing about xenon is it's one of the biggest noble gases. Well, the biggest noble gas is going to have the lowest ionization energy. So if you have a powerful enough oxidizer, it can oxidize it and form a compound. So we take fluorine, a powerful oxidizer, and we can form a xenon-fluorine compound. And so what we're going to do is we're going to put the two fluorines in the axial site because there are 3 lone pairs here and 2 bonds, so 5 altogether. And so 1 lone pair is going to go in plane in this equatorial site. 1 lone pair is going to stick out here, and the 3rd lone pair is going to stick in here. And so this forms a trigonal planar arrangement of lone pairs. We have the 2 axials here. There's only 1 bond angle. It's the XeF angle. And it's going to be 180 degrees. We don't expect any distortions because the trigonal planar is circularly symmetric. You know? And so this is going to push it up, this is going to push it down, that's equal and opposite, so no distortions, 180 degrees. We call it linear. Linear. So we got to lay it. Okay, the next thing we're going to look at is when we have 6 groups around the central atom. If we have 6 groups, then it adopts this configuration. We have these 2 at 180. But rather than having 3 groups in the plane, we're going to put 4 groups in the plane, which is going to distort it like this. And so 2 of the groups will come out, 2 of the groups will go in. This group geometry is called octahedral. Octahedral has spherical symmetry, like tetrahedral. And so we could build it. That's the group geometry. Let's look at some molecular geometries here. And so the first molecular geometry we're going to look at is octahedral. Octahedral, octahedral. We're going to look at SF6, sulfur hexafluoride. If you look at sulfur hexafluoride, sulfur is in the middle, and then we have 6 bonds to it, no lone pairs. And so it adopts an octahedral shape like this. It's called octahedral. Octahedral's 8. It's called octahedral because if you connect all these fluorines and make a polygon, you know, then it would be an 8-sided polygon. It would be an octahedron. And so we just connect them. All the bonds are the same. There's no axial and no equatorial because if you grab them, they all have 3 90s and 1 180. And so it doesn't matter which fluorine you grab, they all look the same. And so the angles, we don't call axial and equatorial. We're going to call it fluorine, sulfur, fluorine. Now we have 2 types of fluorines. We have the adjacent ones at 90, and then we have the opposite one, only one of those at 180. And so we go fluorine, sulfur, fluorine, opposite. So that angle is going to be 180 degrees. And then we'll do fluorine, sulfur, fluorine, adjacent. And it doesn't matter which one you pick, there's no axial. All these are axial positions. All these are equatorial positions. They're all the same. This one's going to be 90 degrees. No distortions in this structure. SF6 forms more bonds than SF4, you know, but we have to expand the octet a little more. And so in this case, we have 2, 4, 6, 8, 10, 12 electrons. So additional 4 electrons. Those additional 4 electrons must occupy the D subshell, if what I told you is correct. And so that's octahedral. The next geometry, molecular geometry that we get is square pyramidal. Square pyramidal is when we have one lone pair. And by convention, that lone pair is written on the bottom. So we could have something like BRF5. Bromine's a big atom. Fluorines are small. And so the bromine gets stuck in the center. And we'll put a lone pair. We'll put the lone pair in the position down. So that leaves these four in the plane here, like this. And then one sticking up here. And so if you look at the shape of this, there's a square plane here, and then this apex. And so it looks like a square pyramid. And that's what it's called, square pyramidal. And so what we'll do is we'll label these. We'll call this one, you know, A, and we'll call these ones B. These are all the same. Here, B. This would be the base of the pyramid here. This would be the top of the pyramid. Lone pair stuck at the bottom. And so when we look at the angles, what angles do we have? We have the A to BR to B angle. The A to B angle here, normally it's 90 degrees, but this lone pair at the bottom is going to push the base up. If it pushes the base up, then it's going to distort the AB angle and compress it, maybe to 88 degrees. Okay, then we have the FB to FB angle. And so the FB to FB angle here normally is 90 degrees. But again, it's probably going to be compressed by the lone pair there, so it's distorted to maybe 88 degrees. Here, build that. You can take a look at the angles by pushing the base fluorines up. Be that. Okay, if we have two lone pairs, like in this molecule, XEF4, two lone pairs and four bonds, we have four groups. And so xenon's going to go in the center, it's attacked by fluorines. Now, if I put a lone pair on the bottom, then I have a choice. I could put the lone pair adjacent to it or opposite. If I put the lone pair opposite, that's going to minimize the repulsion. And so I put the lone pairs opposite. This looks like axial, but it's not. It's octahedral, it's spherically symmetric. And so it's just best to put them opposite. And it could be in the equatorial, it would just be opposite in the equatorial here. And so there is no equatorial axial here. So let's put the lone pairs on the fluorines here. And this is called square planar. Because it turns out all these atoms are in the same plane, and it has a square arrangement. And so one way square planars are often shown is by just putting it all flat on the page. And so now all atoms are in the plane of the board. And so that means one lone pair has got to stick out, and one lone pair sticks in. So one lone pair is coming straight out, the other is going straight in. Whereas these two lone pairs are in the plane, and all the bonded atoms are either coming out or going in. And so these are the same structures here, square planar. We only have one angle. The FXEF angle is going to be 90 degrees. Because, you know, if this is pushing it down, this is pushing it up, and they're equal and opposite. in distortions. So the distortions cancel. And that would be XEF4. So what do we need in order to define the shape of a molecule? There are two things we need to define the shape of a molecule. We need the bond angles and the bond lengths. If we know the bond angles and the bond lengths, then we have the three-dimensional shape of the molecule. And the last part of chapter 10 talks about bond order and bond length. So let's take a look at some of these bond lengths here. I see the shortest bond is 74. That would be for hydrogen. The longest bond would be iodine, 266. Iodines are big atoms, so two big atoms bonded together is going to have a pretty long bond length. Bromine's smaller, chlorine's smaller, fluorine's smaller. And so you can see how progresses here. The same thing. Iodine's biggest, bromine's smaller, chlorine's smaller, fluorine's smallest. Bonds get shorter, atoms get smaller. Okay, sometimes when we have the same atom, like this, two carbons, the two carbons single bond, 154, double bond, 134, triple bond, 120. And so as we go from single, double to triple, the bond gets shorter and shorter. And so what we can say is a single is what we call a bond order 1, doubles bond order 2, triples bond order 3. Bond order is just the number we ascribe to the bond. As the triple bonds are the shortest, we see that this is homonuclear, this is heteronuclear, carbon and nitrogen. You see the single bonds the longest, the triple bonds the shortest. Carbon-oxygen bond, single, longer than double. Here, nitrogen, triple bonds the shortest. Here. Bond lengths range from about 100 to 300 here. Let's take a look at the bond energies next. The smallest, let's see. Smallest, the longest bonds are usually the weakest. And so, like an iodine bond is very long, 266 picometers, and it's weak, 151. The fluorine bond's a lot shorter, and actually fluorine's kind of weak. Chlorine's a lot shorter, it's a lot stronger. Fluorine's kind of out of the pattern here. What's the weakest bond that you see? Weakest bond doesn't turn out to be the biggest or the longest, iodine. It turns out that this is the weakest bond. The OO bond. The OO bond is special. We call it what do you call an OO single bond? Peroxide. Peroxides are unstable, so you try to avoid forming them because at 142 kilojoules, visible light can easily break that bond. And so peroxides have to be protected from light. Iodine also has to be protected from light. Bromine, maybe. Maybe you should protect that from light. A lot of these other bonds are a lot stronger. What's the strongest bond you see? The nitrogen-nitrogen triple bond. This is exceptionally strong, almost 1,000 kilojoules per mole. And that's why nitrogen is considered a pseudo Nobel gas or an honorary Nobel gas, because it's so unreactive. It costs way too much energy to break that bond. It's very strong, short bond. All right, let's take a break here and then almost done.